Hello, George Romanic here. Today we are going to talk about Coriolis force affecting moving charges in a conductor, namely influence of the Coriolis effect on electrical current. Text of the problem is now on your screen. So here is the setup of the problem for today. Before we start solving it, please, you can disregard the left part of the blackboard. This is from the previous problem where we calculated the velocity that a car needs to have to fly thanks to the Coriolis force. So you can check that video if you want. But here we have another problem where we have a wire and the length of the wire is L, 1 meter. Wire is somewhere, let's say in Montreal, 45 degrees north, and there is direct current through this wire, and current is 10 amps. Now, these are constant. This is mass of an electron and charge carried by electron. Charges of electron is negative, but we are not interested in signs over here, so we can just take absolute value. So what is current? Well, there is a bunch of electrons in this wire. If this is, let's say, copper wire, and these electrons are, let's say, moving in this direction. And these electrons carry charge, and that charge that passes through, let's say, this cross-section is current. And the current is 10 amps. And the velocity of these electrons is called drift velocity, Vd. So what would be, now, because these free electrons are moving in the wire, that means there will be Coriolis force acting on them. So let's see what is the Coriolis force acting on one electron, just one electron. In absolute values, absolute, so I don't have to think about plus and minus. I'm just interested in intensity. That would be, we know expression for the Coriolis force. Mass of electron, mass of the object, in this case electron, times the Coriolis parameter f, and times the velocity of this these electrons Vd. So we take drift velocity, we take intensity of this. And you know from previous videos, hopefully, that f is Coriolis parameter 2 omega sine phi. So phi is latitude, I know that, and omega is angular velocity of the Earth, approximately 7.3 times 10 to power negative 5 radians per second. So this is force on one of these electrons. But I'm not interested in one of these electrons, I'm interested in all electrons that are in this wire of length 1 meter. So to get that, I will introduce a variable that I will call n. And that is number of electrons, per unit volume, and that would be cubic meter. So this is number of free electrons, let's say in this copper wire, per cubic meter of copper wire. But I don't have cubic meter here necessarily. I have what I have. I have this wire length of L, and I don't even know cross-section. So we can see, therefore, that Coriolis force of all these electrons is equal, if this is Coriolis force of one electron, then the number of electrons in this wire over here needs to be n times the volume of this wire. Now I will say that cross-sectional area of this wire is A, n times L times A. This is the number of electrons in this wire of 1 meter. because n is number of electrons per cubic meter, and here instead of cubic meter I have L times A, volume. And then times ME times F times VD. So this would be Coriolis force of all these electrons that are drifting in this wire. However, I don't know A, I don't know N, and I don't know VD, drift velocity. But what I do know is the current. And we will now make use of that. How are we going to make use of that? Well, notice that NLA, let me write this actually. I want to make clear. NLA, this variable is number of electrons in my wire. In my wire. Therefore, if I multiply this by E, charge of one electron, so E NLA would be amount of charge that is moving through this wire. So, because each of these electrons carries one charge, so I multiply number of electrons by their charge, I get total charge moving in my wire. I hope you can, so charge moving in my wire. That's this. And generally, we call this Q. So Q is this variable. But I know that electric current is charge that is moving through wire, which is this, in some time t. Which means that Q is equal I times t. T is time. Now I don't know time, but I know that time can be expressed in terms of the length of the wire and drift velocity. So I, and instead of time, I say that is L divided by VD. Basic kinematic equation for velocity. Velocity is distance over time, therefore time is distance over velocity. Now let's combine what we have here. Let's go here. F Coriolis is equal NLA would be Q over E. So I have Q over charge of an electron, that's this, times mass of an electron times Coriolis parameter times drift velocity of these electrons. Or F Coriolis is equal Q is I times L divided by VD. So notice that this VD and this VD therefore will cancel. And I will have here I times L times mass of electron times Coriolis parameter divided by the charge of one electron. And this is Coriolis force exerted on this wire due to motion of the electrons, namely due to current of 10 amps going through the wire. So if you plug in numbers over here, so 10 amps times 1 meter times 9.1 times 10 to power negative 31 kilograms. Now F is approximately 10 to power negative 4 second minus 1 if you calculate here F. So you plug in this number and E is given 1.6 times 10 to power negative 19 coulombs, then you get that this Coriolis force due to all these electrons, I have it somewhere here, is 5.7 times, of course approximately, this is approximately 5.7 times 10 to power negative 15 newtons. This is exceptionally weak force, exceptionally weak force. However, and that's why when electrical engineers are designing system in this room, they weren't considering Coriolis force because, well, first of all, most of the current here is alternative current, but even if it was direct current, the Coriolis force is so negligible that it just doesn't make any sense analyzing it. Just to show you how negligible it is, here I calculated Coulomb force between two electrons. So Coulomb force between two electrons that are at the distance of a radius of a diameter of a hydrogen atom, which is approximately 10 to power negative 10 meters, is 2.3 times 10 to power negative 8 newtons. So if you think about it, repulsive force between two electrons is 7 orders of magnitude larger, two electrons, than the Coriolis force of all these electrons combined in this wire. That's why electrical forces are really, really nasty. There is no joking around with electrical forces. You can see how strong they are. Just between two electrons. Here, Coriolis force is not even to be mentioned for all these electrons. However, it is interesting to think conceptually this exists. So electrons moving in these wires around me, they feel the effect of Earth's rotation. No matter how minimal that effect, they feel it. And that's something absolutely amazing. Of course, let's analyze this equation. You can see if the length of the wire increases, Coriolis force increases. Well, that makes sense. Because if we increase length of the wire, we said that Coriolis force depends on the distance. Well, there is more distance for the Coriolis force to act, and therefore Coriolis force increases. If we increase mass of electrons, which we cannot, but if the mass of electrons, if the electrons were heavier, well, Coriolis force would be larger because force depends on mass, inertia. If the Earth was, think about this, if the Earth was rotating faster, Coriolis force on electrons would be higher. So maybe on some other planet that is rotating really fast, Coriolis force can be so high to be comparable to electrical forces. I don't think so, but conceptually possible. And of course, if the current is larger, Coriolis force is larger. What would that mean? Well, if the current is larger, means there is more of these electrons passing, free electrons passing through the wire, and therefore they increase the effect of the Coriolis force because we are interested in all these electrons that are passing. And if the charge of electron was larger, the Coriolis force would be weaker because you have stronger, maybe, repelling force among electrons. So this is very interesting concept that crossed my mind, and I decided to make problem and share it with you. What you can do now, think about this, and maybe let me know in the comment section below. You can think about what needs to be some of these parameters, let's say maybe rotation of the Earth or current or length of the wire, so the Coriolis force is 1 Newton. 1 Newton is something we could measure easily. So what would have to be, current number of electrons passing for the Coriolis force to be 1 Newton. Until next video, goodbye.